All right, the next example we have is example 3, and we are asked to find a general expression for the nth order derivative of the following functions. So effectively what we're trying to do is get a formula that if we know we want the 30-second derivative, we can just substitute into the formula n equals 32, and then out would pop out this 30-second derivative without needing to take 32 derivatives in a row. So in order to do this, we're trying to get a pattern and write down a formula. So to do this, organization is key, and writing things in a certain way, sometimes writing things in 2 or 3 different ways so that you can try to see the pattern. So this one is very straightforward compared to some of the other ones you could see, such as in part B. This one gets a little bit trickier. But let's start with this x e to the x. So first column we'll write n, where we're going to have numbers, whole numbers, starting as 0, and then 1, 2, 3, so on and so forth. Next column we'll have fn of x, and a little notational thing here, we're used to using the prime notation. So if we had like f triple prime, this would mean the third derivative. Well, we could also denote the third derivative by writing it surrounded in parentheses as a superscript. So that would also mean the third derivative. So this is saying the nth derivative, effectively. So for the 0th derivative, that's just the original function. Because if we've taken 0 derivatives, then that has to be the original. So for the first derivative now, we're going to take a derivative of the previous cell in this second column. So in the previous row, we'll differentiate that expression. So we'll have derivative of the first times the second left alone, plus the first times derivative of the second. Now sometimes it's useful to notice, not always, but it's useful to notice if things repeat. So here, x e to the x is exactly the original function. So sometimes it's useful to write things like, oh, e to the x is, the first derivative is just e to the x plus the original function. Sometimes that's useful. Okay. So now, as we keep going here, let's actually rearrange this slightly differently. Okay. So the next column, or the next row, 2, the second derivative, we can take a derivative of this expression. But that seems like some redundant work because we've already taken the derivative of this. The derivative of this is this whole thing, right? Because we took the derivative of this to right here. So there's a lot of redundancies here, so be on the lookout for that. You want to avoid doing the product or quotient rule, 20 times. So in here, what I would notice here is that since this is the same as this, I know that to get here, we need to differentiate this expression. So the derivative of this red expression is e to the x plus, well, the derivative of the 0th derivative must be the first derivative. And we know that the first derivative here is just what's contained in this column, which is, so we have e to the x plus, we have the first derivative, which is e to the x plus the 0th derivative. So it looks like the second derivative is 2e to the x plus the original function. And then we can go again to calculate the third derivative. So if we do the third derivative, let's go ahead and just differentiate this expression. Well, that would be 2e to the x plus the first derivative. And we know that the first derivative is e to the x plus the original function, which, collecting like terms, is 3e to the x plus the original function. So there's a certain point, usually around the third or the fourth derivative, that people start to see the pattern. Some people might be able to see it here. Some people might have to go to the 5th or maybe even the 6th, but usually 3 and 4 is our sweet spot for the pattern. All of these you should be able to see by the 3rd or 4th, and if you can't see anything, it either means you're making some sort of mistake or maybe you're writing things in a way that's not helpful. I see lots of people who just write out these long, big expressions because they never bothered to collect these like terms to simplify e to the x plus e to the x equals 2e to the x. They just left it, I've seen people down in the 5th derivative where they just have e to the x plus e to the x plus e to the x, and it's just a mess. Remember that if you're trying to find a pattern, organization and simplification is key. So at a certain point, you're going to convince yourself that you have found the pattern. So what I'm going to go ahead and do here is just put some dots because I'm convinced I know what the pattern is. And I'm going to say that the nth derivative is going to be n times e to the x plus x e to the x. There you go. And that's it. For part B, that was part A. For part B, we're going to do literally the same thing. So we'll start our table. So we have an n column, 0 column, and then we're going to have our nth derivative column. And here we're going to have the original function, right? And also for this one, because we're going to be doing lots of derivatives, I'm going to choose to write this as x to the negative 3. So then, when we get to the first derivative here, n equals 1, this would be negative 3x to the negative 4. Second derivative will be, well, here negatives are going to cancel, and we're going to have 12x to the negative 5. Now, there's something that's going to show up in a lot of these problems, not all of them, but a lot of them. It didn't show up over here in part A, but it will show up here, and that is factorials. Factorials, we'll do a little aside here about factorials in case you haven't seen them before. So 4 factorial is 4 times 3 times 2 times 1, which is 24. 10 factorial is 10 times 9 times 8 times 7 times all the way down to 1. That's what a factorial is. And when you're doing certain types of derivatives, factorials show up a lot. So down here, instead of actually writing this as 12, I'm going to choose to write this as 4 times 3 times x to the negative 5. And then when I get to my third derivative, we're going to have negative 5. So it's going to be negative 5 times 4 times 3 times x to the negative 6. And sure, we could have written, negative 60 when we multiply negative 5 by 12, but that's not going to help us see the pattern. We're going to get these seemingly random numbers. They're not random, they're the result of factorials. So what we'll do here is I'll do one more, and we'll have 4. This will be positive 6 times 5 times 4 times 3 times x to the negative 7. So this pattern's a lot harder to see. A lot harder to see. Because here our n value is 4, but there doesn't seem to be any specific connection to 4 in here. At least not readily visible. So there are a couple components here we want to discuss. To me, there is the sign that we have to deal with. It goes positive, negative, positive, negative, positive. It's alternating sign. We then have the actual coefficient, 1, 3, 12, whatever this is, whatever that is. I already mentioned this factorial thing, and that's going to be our link here. So what I would do here is I would write this as, let's take a look at this one right here. We know that 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So although it's not 6 factorial, what are we missing really? We're missing the 2 and the 1. And in fact, this right here does also appear to be pretty close to 5 factorial. 5 times 4 times 3. But again, we're missing the 2 and the 1. And in fact, we're missing that on pretty much all of them. One thing I also want to mention here is that when you're trying to develop a pattern, a lot of times your pattern will work for the derivatives, but it won't necessarily work for the original function. Sometimes it does, like over here, we were able to get this to work out, right? If we actually plug in 0 for n, this term goes away and we do recover the original function. Don't necessarily expect your pattern to do that. The problems you'll see, they will work for this, but sometimes getting this to work out can be a little tricky. So let's just not worry about that. Let's focus on n equals 1 and above for now. So what we could actually do here is notice that 2 times 1 is just 2 factorial. So it looks like this is actually, let's go ahead and erase this for now. We can actually say that this is equal to negative 5 factorial over, now you can write 2 factorial or you can just write 2. I'm going to write factorial because if I had given you a different starting function, so maybe instead of 1 over x cubed it was 1 over x to the 7th, then we'd have a different factorial showing up. So I'm going to choose to do that. So this would be negative that factorial. And then this would be x raised to the negative, what is this? 6. So in relation to 3, this is 3 plus 3. And what's this one look like? This is positive 4 factorial over 2 factorial x to the negative 3, so 2 plus 3. This is equal to negative 3 factorial over 2 factorial x to the negative 1 plus 3. And now does this work? Let's check. I don't know if this is going to work, so question mark. Is this going to work? This would technically be 2 factorial over 2 factorial, if we're following our pattern, x to the negative 0 plus 3. That does seem to check out. So here, this would be, it seems, (6 factorial over 2 factorial x to the negative 4 plus 3. So it looks like we have this figured out. So it looks like for us, the pattern seems to be x to the negative n plus 3. And then we know we're always going to have division by 2 factorial, but we need to somehow relate the factorial in the numerator, so this starting number, we have to relate it to here. So notice that 6 is 2 more than 4, 5 is 2 more than 3, 4 is 2 more than 2, 3 is 2 more than 1, and 2 is 2 more than 0. So it seems that the numerator here is actually n plus 2 factorial over 2. Okay, that's good. But now what about the sign? Well, something that we're just going to have to tell you is if you take negative 1 and raise it to a whole number power, negative 1 to the 0th is 1, negative 1 to the 1 is negative 1, negative 1 to the 2 is positive 1, negative 1 cubed is negative 1. Basically, negative 1 to an even power is positive, and negative 1 raised to an odd power is negative. So we just want to make sure we have this right. We want the even numbers to be positive in this case, right? 0's even, positive, 2 positive, 4 positive, 1 and 3 are odd, they're both negative. So this checks out. So if it happened that the evens were negative, then instead you could just do something like negative 1 to the n plus 1, just shift it by 1. So then when you plug in n equals an even number, by the time it makes it in here, we shift it up to an odd by this addition of 1, and then we get a negative. So you can always just manually adjust it so that whether it's even or odd, you get the right desired number. So that's the pattern. So ... the nth derivative of x is negative 1 to the n plus 2 factorial over 2 factorial x to the negative n plus 3. And that's it.